This video will take a look at ionization energy as it applies to the AP exam. In particular, what can we learn from measuring the amount of energy required to make an ion? First, let's define ionization energy. The energy required to remove an electron from an atom. Energy can be added as heat, light, or electricity. Generally, light is preferred because it's easier to measure the exact amount of energy required. So an atom, energy is added, an ion would form, and then the electron and ion forms because the electron is removed. So let's take a peek at first ionization energy. First meaning, we should first say first meaning the energy to remove one electron. And the electron that would be removed, of course, is the easiest one. So let's take a peek look at what this means and the trends that we see in the periodic table. Lithium, a fairly low value. As you go across the chart, you'll notice that that increases. Or if we start with beryllium and go down the chart, you'll see that that decreases. And that across the chart increase will happen in any of the rows in the periodic table, from 496 over to 1500 for argon. And pick any column, and the ionization energy will decrease down the column, 1400 for nitrogen, down to 703 for bismuth. Let's take a little bit closer look. The decrease down the chart, it's easier to remove, or less force is required. We need to be able to justify that on an AP exam, and so we want to say because the valence electrons are occupying, that's important, energy levels that are further from the attractive force caused by the protons in the nucleus. And so the distance, if we apply Coulomb's law, which AP would love for you to say, the distance between the protons and the valence electrons, if that is greater, as is the case when you go down the chart, the force required to remove those electrons would be smaller. Let's take a closer look. As we go across the chart, the ionization energy increases. What does that mean? That the electrons are harder to remove, more force is required as we go across the chart. This, we again have to be able to justify. This is due to the fact that the number of protons is increasing. And those electrons are in the same energy level. If you pick any particular row in the periodic table, the electrons are all in the same energy level. Another way of saying the same thing is effective nuclear charge is increasing across the periodic table. I know there's some blips, we'll take a look at those, meaning the nucleus or the protons are increasing as you go across the periodic table, so the force required according to Coulomb's law would be greater. We'll take a look at anomalies either later in this video or in another video. First, let's take a look at successive ionization energy. What exactly does that mean? Well, scientists said, heck, if we can learn something from knocking off one electron, what might we learn from trying to knock off another one and another one? Let's take a peek. Successive ionization energy is the amount of energy required to repeatedly remove electrons one at a time, one after the other. So not knocking all the electrons off, but one at a time. For instance, if we take an atom and we add some energy and produce this ion and the electron is removed, let's now take that ion, add some more energy, and a 2+ cation would form as the next electron is removed. And the third ionization energy would be taking that 2+ cation, adding still more energy, producing a 3+ cation as that third electron is removed. But first, which ionization energy would be larger? The first ionization energy of magnesium, here it is in the periodic table, or the second ionization energy of magnesium? For that matter, for any atom, the first or the second, would the ionization energy be the same or would it be larger? Let's take a look. It might be helpful if you drew a Bohr diagram, pause and try to answer, and then check as we proceed. So which ionization energy would be larger is the second ionization energy of any element will be larger than the first, and the third would be larger, the fourth. Every successive ionization energy would be larger. But let's take a closer look as to why any given one is larger. And so first of all, losing one electron reduces the amount of repulsion between valence electrons. So magnesium has two valence electrons. As the first electron is removed, the second electron remaining will be closer to the nucleus because of the reduction of repulsion, which allows the electron that's remaining to scooch, that's a highly technical term, a little bit closer to the nucleus. That would then make the second electron that is removed, because it's a little bit closer to the nucleus, it would make the second electron would need more force in order for it to be removed. Now, as I said, every successive ionization energy will be greater. But how much greater? Let's take a closer look at that. So this is a lot of numbers on one page, but notice as you go down the side in blue, that corresponds to this blue, this second period in the periodic table. Here's the first period. And then in green, I've highlighted what would be the third period. And so let's take a close look. Notice that beryllium would be 500 and the second would be 7,300. Great. But, sorry, for lithium. For beryllium, 900. The second one, not quite triple, but whoa, look at the third ionization energy, 15,000. Of course, the fourth is a little bit bigger still, but not a large increase. That same trend happens down with magnesium. The first ionization, 700. The second one, double with 1,400. And the third one, much more than double, probably 5 or 6 times greater than the second. Of course, if we look back up, boron, 900, 2,400, not quite triple, not even double. For 3,600, then, whoa, 25,000. So what's causing these, of course, they're highlighted in red, what's causing these interesting, very large increases over previous ionization energy? So one might want to say, why is it that lithium's second ionization is so much larger than its first? But why is it for beryllium, its third ionization energy is so much larger than its second? Fill in a Bohr diagram for each element, here they are on the periodic table, and try to answer and before we proceed. Let's take a look. So there's a Bohr diagram at the bottom for each of the elements, lithium and beryllium. And so lithium has one valence electron, which you should know by seeing that lithium is in the first column of the periodic table. And when that first electron is removed, a certain amount of energy is required. But then trying to take the second electron, now it is one, it's the next energy level closer to the nucleus, and will experience a greater attractive nuclear force, a much greater attractive nuclear force, because it's closer and it would be a higher effective nuclear charge. Even though the nucleus hasn't changed, there's no electrons in between these electrons, this next second electron for lithium that is being removed. Whereas for beryllium, the first electron is removed and it costs some value. I don't have it memorized. The second one removed would cost a little bit more, as represented by my slightly bolder arrow. But then the third electron that's removed now is in the first energy level, meaning that the third electron of beryllium is in the next closer energy level, experiencing a much greater nuclear attractive force. So you should try to think about, well, for boron or aluminum or gallium, which ionization energy would see a very large increase? Well, there are 3 valence electrons, and so this would happen at the fourth. The fourth ionization energy for boron, aluminum, or gallium would see a very large increase. It's an easy way to remember. And so a very large increase will always occur one more than the number of valence